In this video, we are going to explore the derivatives of two trig functions, sine and cosine. So let's get started. So it turns out that the derivative of cosine of x is minus the sine of x. So that's already pretty neat because you take the derivative of one function, one trig function, and you get back another trig function. So now we can kind of do a loop here. Let's see what is the derivative of minus the sine of x. So the derivative of minus sine is minus cosine. So that's pretty funny. We get back to this, and you can already see that this is going to go in a circle. So we take the derivative of minus cosine, and that gives us plus sine. And then, of course, the derivative of sine gives us cosine. So we've started with cosine, taken its derivative, and then a derivative, and then a derivative, and a derivative, and we end up back at the original function. That's pretty neat. I have always remembered this cycle of trig derivatives using this little image here. So we have cosines up and down, and sine left and right, and then the negative signs are here. Like if you think of drawing a diagonal line here, then below and to the left of the diagonal are negative, and above the diagonal is positive. And then you just have to remember that the derivatives flow this way. I'm going to talk about integration in a few videos, and then the arrows actually flow the other way. But anyway, I don't know if this little picture helps, but that's the way that I have always remembered these cycles of derivatives. What I'd like to do in Python is show you this cyclicity of these cosine and sine derivatives, and then use SymPy to generate some plots. So we are going to need SymPy and display and math for LaTeX printing. Amazingly, we are not going to be using NumPy. This is probably the first video in ages that we're not using NumPy. Okay, so let's start off with I use X all the time. I mean, X is a great letter, of course, but it's good to like change things around a little bit. So Q equals symbolic symbol for Q. And now I'm going to write out sim.diff, so the derivative of sim.cosine of Q. And here you go, just as I claimed in these slides, it is minus the sine of Q. And then let's try again for sine, and then we get that the derivative of sine is cosine. Okay, so to show the cyclicity, what I'm going to do is basically have a loop. It's going to be a loop that's just continuing to compute the derivative of what goes into the loop and then print out what that derivative is. So let me show you how this is going to work. So I'm going to define a function. Let's start off with cosine of Q, and then let's see, for I in range 0 to, how about 8? So we'll go through this cycle a total of 8 times. So I'm going to display, so what I want to do here is print out the original function and then print its derivative. A fraction d by dx of %g, our s, and then this is going to be the function, equals %s, and then I will replace that with the derivative. So let's see. So this first replacement is going to be LaTeX version of the function here. And then the next substitution here is going to be the LaTeX coded version of the derivative of f. Okay, so let's just run this code. Now, so far, this is not terribly interesting. Well, the first line is pretty interesting. Everything else is quite redundant. So what I'm going to do now is update this variable f. So I'm going to say f equals sim.diff of f. So now notice that although f starts off as being this expression here, each time we run in the loop, at each iteration of the loop, f is going to become the derivative, which means that at the first iteration of the loop, f is cosine of q, but then at the second iteration of the loop, f is going to become the minus sine of q. So now when we run this, you can see that cosine goes to minus sine to minus cosine to sine and then sine back to cosine. We've gone full circle, and then I don't know why we go full circle twice. Okay, so that is for algebra. There's just a bunch of letters and lines and curves and things like that. I would like to see how this looks in pictures. So therefore, what I'm going to do is put these 4 different components, so cosine, the original function, and then all of its derivatives, into the same plot. And to do this, I'm going to use the SymPy plotting. And as I've done in previous videos, I'm going to create a shorthand to access sympy.plotting.plot as simplot. So that's just going to make things a little bit cleaner for the code so I don't have to write out all of this business. All right, so let's start again, resetting f to be sim.cos of q. Now I'm going to loop again, except now this time it's not going to go in 8 steps. We're just going to go through this loop once. Okay, so what do I want to do? I want to say something like p.extend and then insert a plot in here. So that means I need to initially define p out here to be simplot. So then the function is going to be f show equals false because I want to put multiple lines, multiple functions into the same plot. And of course, we're going to need a label so we can differentiate all the different lines. And that's going to be the LaTeX version of f. Now, this is fine. You can define this first plotting object here outside the loop. And then inside the loop, you just extend, use this method extend, which means to add more lines to this plot that p refers to. However, I'm going to show you a different way to set this up. So I'm going to write if I equals 0. So this happens on the very first iteration of this loop. So on the first iteration of this loop, that's when we actually generate the first feature of this plot, the first line in this plot. Else, then we are going to extend it if I is not equal to 0, which means basically if we are already moving through this loop after the first iteration. Now, sometimes it's easier to set up code this way, so you get everything inside the for loop. Sometimes it's easier to set up code the way that I showed before, where you start initializing some features of the plot before you get into the loop. But it's good to know about this possibility in case it's useful in the future. All right, anyway, simplot f and then show equals false. And then again, label equals sim.latex f. Now, here I'm going to run into the same problem that I had up above, which is that if I don't update f, then I'm actually just replotting the same exact function over and over and over again. So therefore, what I want to do is redefine f to be the derivative of f. Okay, and then let's say p.show. And of course, I added some line labels here. So I need to write p.legend equals true. Okay, so let's run this. Okay, so the error is on this line. And actually, this error comes from putting an end parenthesis too early. So you can see that the way that I've set this up now, which is wrong accidentally, is that the label actually goes into the second argument, the second input of the extend function, which is not what it's supposed to be. The label is supposed to be associated with simplot. All right, now let's try this. Okay, so it's kind of a nice looking pattern, I guess, but we can't really see which lines correspond to which, and they kind of cycle through a bit too much. So let's see, I'm going to change the x-axis limit from, let's try -3 to 3 and see how that looks. Okay, so that looks a little bit better. Now we need to adjust the colors to make sure that these are actually differentiable from each other. So how should we set the colors? Well, we have 4 different lines, so we need to have 4 different colors. Now, there's a couple of ways that you could set this up. We could come up with some variable like this and say, you know, black, red, blue, green. And then here I can say line color equals colors and then the ith element in colors. So that's going to work. Of course, it doesn't work for these other lines because I haven't put it here. But I would like to change this. I would like this to be a little bit more dynamic, to be based on I itself. So what I'm going to specify is that the colors should be I divided by, and let's try the maximum value here. So I divided by 3, I divided by 3, and I divided by 3. So let's see what this is going to look like. So copy, and then also have to put that in here, making sure I don't make the same mistake twice of putting this line color after the end of the simplot function. So it looks like we're missing a line. Actually, what's happening here is that the sign, the line for sign, is white. You can actually see it's broken here and here as it crosses through these functions. Okay, so dividing by the maximum number of iterations isn't good because then we end up with a number of 1, which is pure white. So maybe let's try dividing by 5. Maybe that looks better. Then should be consistent here. Okay, that looks a little bit better, except now they're still a little bit hard to distinguish because they're all grayscale. What if we would do something like this? What if I made the middle one, which corresponds to green, divided by 3? Aha! Now this is looking better. Now we can see all 4 lines, and they all have a nice shade of green. In this video, you learned about the cyclic nature of the derivatives of sine and cosine, and I hope you got a bit of a review about SymPy plotting. Maybe you also learned a couple of new things. Of course, there is an exercise associated with this video, but in the interest of time, I didn't want this video to go on forever, so I decided to put the exercise into the next video. So stay tuned. Go, get a sip of water or whatever, come back with your thinking cap on, and get ready for the exercise.